Hi, it's Miss Parrott, and welcome back to the series AP Biology Equations Explained. This is the third in the series, and today we're going to be diving into standard deviation and standard error of the mean. Now, whether you're a student or a teacher, you may be wondering, why do we have to do statistics in biology? Aren't mean, median, mode, and range enough? And the answer is no. Biological systems have a lot of natural variation, so we have to use statistics to quantify the variation and then to determine, is that difference significant or could it be due to random chance? It helps us to be good scientists. Let's first look at standard deviation. Standard deviation helps us quantify the spread of the data points from the mean. This is the formula. It is provided on the AP Biology formula sheet, so you don't have to memorize it. Standard deviation is S, and we're going to take, this looks kind of intimidating, but we're going to break it down. Remember, all the variables are defined on the formula sheet as well, in case you forget. But the square root of the sum of all the individual data points minus the mean squared. So say you have 5 data points. You're going to take that data point, subtract the mean from it, and square it, and then add all those up. Then divide by the degrees of freedom, which is n, the number of trials or individuals or groups, minus 1. And if you have a small standard deviation, what that means is that your data points are clustered pretty close together, giving you some pretty high precision. And if you have a large standard deviation, that means your data points are much more widely spread. Now, we need standard deviation to calculate standard error of the mean. Standard error of the mean quantifies the reliability of a sample mean as the estimate of the true population mean. So on the formula sheet, you'll see this as SE or SE sub X bar, which means standard error of the mean. This is the formula, much more simple. So standard error of the mean equals standard deviation divided by the square root of n, or your sample size. This n is very important because, think about it, if your sample size is large, n and standard error are inversely proportional, right? This is in the denominator. So the bigger n gets, the smaller our standard error of the mean is. And the smaller our standard error of the mean is, the more precise and more reliable our data is. And the larger our standard error of the mean, the less precise it is. And the less reliable it is to be an estimate of the true population mean. Now, more often than not, standard error of the mean shows up on the AP Biology exam as error bars on a graph. Line graphs can have error bars, bar graphs can have error bars, anything on an XY axis can have error bars. And so what's important is that you know how to interpret those. So first of all, you would see groups or points with these I bars. So in this case, we have a bar graph. So the top of the bar represents the average plant height in centimeters. So let's say in this example, the fertilizer group had a mean of 15. Now, let's say after doing all those calculations, we figured out that standard error of the mean was 2. So then to draw a standard error bar, you're going to add 2. So if the mean is 15, then this we would draw up to 17. And this one, we would go minus 2 down to 13. Okay, so that's sort of like either how to make it into a graph or what that graph is showing by using I bars. Now, when it comes to interpretation, one of the most important things you want to look at is, do they overlap or not? So if your I-bars do not overlap, that suggests that the difference in the mean is statistically significant. So in this example, fertilizer is likely having a real effect. And the fact that all these are so much taller isn't just due to random chance. So this would be evidence that the fertilizer is working. And we would reject the null hypothesis that it wouldn't make a difference. More on null hypothesis in the next video on the chi-squared test. Now, if our error bars do overlap, so we have two groups and they're very widely overlapping here, this suggests that the difference is not statistically significant and that the difference could be due to just random variation and chance. In that case, we would fail to reject the null hypothesis. Now we're going to go over the steps for calculating standard error of the mean. Then we're going to work a real example, and then we're going to wrap it up. So to calculate standard error of the mean, we need both the formula for standard deviation and the formula for standard error, which can be found in the top left of page 1 of your formula sheet. So first, you're going to calculate the mean. Then you'll make a table to help you break this section down, the x sub I minus the mean, and then also those values squared. Then you want to add all those up. So do this step. Plug everything into here, calculate the standard deviation. Then use your standard deviation and divide by the square root of n to find your standard error of the mean. Let's work an example. All right, before we get started, remember to have your calculator with a square root button and a pencil. So, in this example, it's an animal behavior example. We are given a data table that shows Daphnia heart rate. Now, Daphnia are little water fleas, and there were 5 individuals in a control group with just fresh water. Their heart rate in beats per minute were measured, and the mean of that is 120. Then 5 individuals were put into a caffeine solution, and their heart rates were measured, and I went ahead and did the mean, and that's 150. Now, on the AP Biology formula sheet, you'll find this formula for standard deviation and this formula for standard error of the mean. Now, let's go through those steps we just did together. We already calculated the mean, so check. The mean for the control group is 120 beats per minute, and n is 1, 2, 3, 4, 5. There were 5 individuals. The caffeine group's mean was 150 beats per minute, and their n is also 5. Okay, step 2 was to set up a table with your individuals minus the mean. So let's do the control together. So I just set it up like this. I put this that's in the parentheses, each individual x minus x bar, which is the mean, right? So each individual x, I'm going to put 120. So everything from the data table, 115, 125, 118, and 122, minus the mean. The mean for this whole group is 120, 120, 120, 120, 120. Then we're going to square it. This is nice because it gives us all positive numbers. So 120 minus 120 is 0. 0 squared is 0. 115 minus 120 is negative 5. Negative 5 squared is 25. 125 minus 120 is 5. 5 squared also equals 25. 118 minus 120 is negative 2. Negative 2 squared is 4. And 122 minus 120 is 2. And then we're going to square that, and that also equals 4. Step 3, you need to take the sum of all of these squares. So 25 and 25 is 50, plus 4 is 8. So the sum is 58. Now, I went ahead and wrote, so our standard deviation of the control group is going to be the sum of all this. So now that's just 58. Ooh, isn't that cute? Divided by n minus 1. N is 5. 5 minus 1 is 4. Now we're going to do what's under the radical first. So, all right, let's see. Or you could do square root. You just got to know how your calculator works. Parentheses, 58 divided by 4, parentheses. And then this equals 3.81 or 3.8. That's that's the standard deviation. Now, to find the standard error of the mean, I'm going to use this formula, standard deviation 3.81 divided by the square root of n, which is 5. So, again, know how your calculator works. And so we can do 3.81 divided by parentheses, square root of 5 parentheses equals 1.7. So 1.7 is our standard error of the mean. Let's do it again, this time for the caffeine group. Looking back at our data table, we've got 5 individuals. All right, our X individuals, 150, 145, 155, 148, and 152. I did an extra. Minus the mean, which is 150, 150, 150, 150, 150. And in this case, right, 0 squared is 0. Negative 5 squared is 25. 5 squared. Okay, so these numbers just so happen to work out negative 2 squared and 2 squared, just like the others. On the AP Bio exam, it might not be that neat, but it might, right? And that's going to give us, when we add them all up, we find the sum. That's going to give us 58. And this is actually then, we'll put it in our, up here. Sorry, so 58 over, in this case, we had the same n, and minus 1 is 4. Same math as before, 3.81 over square root of 5 equals 1.7. Now, you might not be that lucky, but even if you get the same numbers, going through the process multiple times is going to help. All right, so what does this mean? If we were asked to draw a graph, we could draw a bar graph depicting the average heart rate in beats per minute of a Daphnia. We have a good title. We have our X and Y axis labeled. We'd have units. We'd have our evenly spaced scale here. All right, and then I went ahead and drew the bars up to the mean, the control up to 120, and the caffeine group up to 150. Now, we're going to add I bars plus or minus 1 standard error of the mean. Now, 1.7 rounds up to 2, and each of our things is 20. So that's just like the tiniest amount, like the littlest I bars, I mean, on this paper. If you have graph paper, you'd make it, you know, closer, even closer than that. So We added I-bars for plus and minus 1 standard error of the mean. And then, so now let's interpret it. Do these I-bars overlap? Well, no, they don't. So, are our differences statistically significant? Yes, it's likely that they are. Are they due to random chance? No, if they overlapped, we would say yes, but they're not overlapping, so we'll say no. And then the null hypothesis, which would state that there's no significant difference, do we reject that, or do we fail to reject it? So we are going to reject it because there is a significant difference in the data. All right, AP Bio folks, here are the key takeaways from today's video. One is that the standard deviation is measuring and quantifying the spread of individual data points, and we note that as S. And that standard error of the mean helps us quantify the reliability of the sample mean. Remember, the larger your N or sample size, the smaller your standard error of the mean, and therefore the more reliable your results. Finally, when reading error bars, if they do not overlap, then you likely have statistically significant results. But if they do overlap, you don't have significantly significant results. Coming up next is the chi-squared test. This is super important in genetics. And in the description, you can find links for the playlist to all these videos from AP Bio Equations Explained, last week's video, and another example of a real life AP Bio Lab example where I work through all the steps. So if you want to see more practice, click that link. And don't forget to like, subscribe, and leave a comment or a question about what you want to see next in AP Bio Explained.